Okay. So as x goes to infinity and as x goes to negative infinity, what value does f of x approach? Well, if x is x to the a. In my case, that would be we're on to the second equation. F of x equals x squared. And kind of look at that over here. We know that the graph of x squared looks like this. So if you go here, here, as x goes to negative infinity, that would be this direction. And x goes to infinity, which means we're going in this direction. And we go this way, negative infinity is this way. We approach infinity by moving, and we move along the x-axis. We approach negative infinity by continuing to move along the y-axis in the negative direction. As we move along the x-axis in the positive direction, what happens to the y value? Well, y goes this way. Y goes to negative infinity this way. So what happens as x goes to infinity, the y value goes to infinity. And as x goes to negative infinity, the y again goes to infinity. So I asked this, saying, as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. Now, why does this work? Well, because if we square x, as we move along the positive x-axis, our numbers get bigger and bigger, and they're positive. If you square a positive number, the first place it stays positive. It is positive. And if you square a big number, it gets really big. Square 100, you get 10,000. Square 1,000, you get a million. Okay. If you move in the negative x direction, the number again gets big, but it's negative. If you square a negative number, you get a positive. If you multiply negative by negative, you're going to get a positive. If it's a big negative number, then you're going to get a really big positive number. And the bigger the negative number gets, the further you get from the x-axis, the bigger that result is going to get. So again, you're going to approach plus infinity. Now your graph shows you that you approach plus infinity here and plus infinity over here. But it's not because of the graph, it's because of what happens when you multiply big positive numbers together and multiply big negative numbers together. What about x cubed? Well, let's put a graph of x cubed. So it's clear from the graph that as we approach, as we move along the x-axis, this just keeps getting steeper and steeper. It approaches infinity faster than this one does because we're cubing these numbers. If we move along the negative x-axis, negative x direction toward negative infinity, approaching negative infinity, our numbers are always going to be negative because, of course, the graph looks that way. But why does the graph look that way? Because when you cube the negative numbers, you get negative numbers. Now, if you're simply involved with the basic functions, you understand that. That's why we started the class with basic functions. So I can say, as x goes to infinity here, y goes to infinity, as x goes to negative infinity, in this case, y goes to negative infinity. And now what about x to the fourth? Well, in the first place, bigger x is, the bigger x to the fourth is. Okay, like the fourth power of 100, 100 is not a hard number to imagine, fourth power of 100 is 100 million, which is a really big number, at least our experience. Okay. So if you take fourth power of a really big number, you get a really big number. So as you move along the x-axis, this thing is going to approach infinity. It's going to approach infinity faster than the x squared function if you do the fourth power. So as x goes to infinity, as x goes to negative infinity, well, you're taking the fourth power of a negative number. And fourth power, well, multiply the number by itself, negative times negative gives you positive, then you multiply it by itself again, you get negative, and then you multiply it by itself the fourth time, and it's back to positive. As x goes to negative infinity, y goes to negative infinity. At x to the d, that's x to the fifth. Well, everything I said about x to the fourth is true of x to the fifth, except that if you multiply a negative by itself 5 times, you're going to get a negative. So as x goes to negative infinity, y has to go to negative infinity. I wrote negative infinity up here. Again, x to the fourth, as x goes to negative infinity for all the reasons I said, y goes to infinity, not negative infinity. Okay, anyhow, so excuse me. So for x to the fifth, as you go to negative infinity, you're going to get a negative. Positive. So you're taking the fifth power of a positive number. And then x to the c, in my case, that's x to the sixth. And it should be obvious as x goes to infinity, y goes to infinity. And as x goes to negative infinity, you're taking the sixth power of a big negative number, the sixth power of a negative infinity. Now make sure you can understand that. Okay. Again, there's some confusion. That's not great. So take that into consideration. 18 mil stuff. Okay. So we got t minus 8 plus b t minus 2. Okay, so see it here. It's minus 8 plus b minus 2. And just in a quick glance, which I think we did pretty well on this one. Okay, so the question asks, what are the q and t intercepts of track? Okay. Well, intercept occurs when t equals 0. Zero equals 0 minus a, and in my case, I will do t minus 4, t plus 5, t minus 1. So we get 0 minus 4, 0 plus 5, 0 minus 9. That equals 180. Positive, because we got some negatives here. Now I think everybody understands this calculation. Okay, there's a Q intercept from t equals 0. The t intercept Q equals 0. So Q equals 0 means this expression equals 0. We have 0 equals t minus 4 times t plus 5 times t minus 5. So this is a product of three numbers. If you multiply three numbers and you get 0, you know that at least one of them has to be 0, right? So every way one of these numbers here, one of these three numbers could be 0, gives you a t intercept. So true when t minus 4 equals 0, or when t plus 5 equals 0. Or when t minus 9 equals 0. So this is true when t equals 4. T equals negative 5, or t equals 9. So now we know this much about the graph of the function. I didn't ask you to graph it, but that would be a simple step. Graph of the function. It looks something like this. You have intercept of t equals negative 5. So that's the point negative 5, 0. T equals 4. Or when t equals 9. Also, your Q intercept, here's T, here's Q. The Q intercept is 180. We have the point 0, 180. Also, think about this. We weren't asked to do this because we asked to graph it, but that's coming up. If t is a really big negative number, then all three of these are really big negative numbers, right? If you multiply three really big negative numbers, you get a totally huge negative number. So that means as you go to the left of the point negative 5, 0, since all of these are going to be negative to the left of negative 5, 0, this product is going to be negative. And as you go to the left, it gets really huge in the negative direction really fast. So we know it's going to come up and down here someplace. It's going to be going down this way fast. Similarly, if t is bigger than 9, all three of these are going to be positive. And as t gets bigger and bigger, they're going to get really big. Three positive numbers keep getting bigger and bigger. So that the graph is going to go up like this over here. Now, t equals 9. So we can construct a graph that comes up from here. It has to kind of gracefully go through this point. So I'm not going to try to, this is not going to be our high point. Our high point is going to be so much below. this. I could test my graph. I could estimate how high this is. And for what t value, it looks like about t equals -2. This thing is about 200. Makes sense? So we need to do an estimate for the graph. So I kind of expect that won't be too bad of an estimate, but I don't expect it to be really accurate. Okay, well, if you put in -2, you get -6 times 3 times -11. Now, -6 times -11 is 66, and 5 times 66, and 3 times 66. I really like that, it's 198. Okay, so my estimate of 200, just by dumb luck, came out really close to what you would get from -2. We don't expect to be that close to the estimates for Hampstead's graph. It's also figure out what my minimum is here, relative minimum. That would be t equals, let's say, 7. And let's see, that's 180, that's about a third of it. I'm going to say -7 or 7. -6. That's great. T plus 5 is going to be -1. And that's going to be -10. It's not -6, it's -60. About a third of 180 is 60, not 6. Okay. So let's say 7 minus 9 is -2. That's -1. And that's 3. So that estimate is really bad. Graph doesn't go down. I did my root table. 3 and 1. I get 6. Should get the 6. Okay. Anyhow, the reason I even mention this is that these graphs get pretty weird and it's hard to draw a really good graph, a really accurate graph. Okay. I left out here, but I would go in there for this. Remember, on 7 plus 5 is 12. Now, okay, so I got 12 times 3 is 36. Times 2 is 72. So negative 72, so -60 wasn't all that bad. Still wasn't nearly as accurate as how it is. Okay, well there we have it. It's a little bit more about polynomials, of course. Next week, we're going to get deeper into polynomials. So think about maybe what you do. That's the place to put this one. This is the third problem, and that's pretty straightforward. Okay, you sketch a curve. When you sketch the curve correctly, it's going to look something like this. Okay. Now, superficially, that looks a whole lot like, and that has a lot of similarities with the curve that we drew here, except it's kind of upside down. If your curve looks like this, then say a couple things. This is f of x. What's it look like as x goes to infinity? it looks like it's gonna go to positive infinity or negative infinity. Give me a thumbs up for positive infinity, thumbs down for negative infinity. Okay, yeah, thumbs down. Okay, most of you gave me a thumbs down. Maybe you're just. Okay, as x goes to infinity. Then x goes to negative. I didn't ask this in quiz, but talking about the polynomial that we're considering. And as x goes to negative infinity. X goes to what? Well, it's going up, isn't it? Negative sign, it ends up going up rapidly, so that's going to be. This is polynomial. Now we can estimate the zeros, right? So we have 1, 2, 3 zeros. If we had a scale on this with numbers and everything, you could estimate the zeros, couldn't you? Not going to say these could be estimated. And it has, of course, a y-intercept. And that could be estimated. And if we did these estimates, we might be able to conjecture a reasonable polynomial function at some points. Well, that comes a little later, but I don't get your brain working on the idea. The question, though, is how many zeros could this thing have? I mean, I'm sorry, what's the minimum degree this equation could have? Well, we've got 3 zeros. Let's say this zero is at that's 1 0. That's 2 0. That's 3 0. Let's just say that this is a 0, 1. Again, if you have a labeled graph, you could estimate these coordinates. So the reasonable equation for this graph might be y equals x minus x1 times x minus x2 times x minus x3. Okay. Because, you know, this is what we just did with one where I did give you the equation. This is just like the equation we just did, except I've got x instead of t, and I've got y instead of q. So if we understand what we did there, we understand if you do x minus x1 times x minus x2 times x minus x3, where these are the intercepts, at least off on the right foot, as far as finding the equation of the polynomial. So this has degree 3. You have to have at least degree 3 in order to get 3 zeros. Okay. Now, another thing is, if you plug in x equals 0, you don't necessarily get this y-intercept. Y1 is not necessarily equal to x1 times x2 times x3. Of course, look at x equals 0, that is what you get. So you might have to put a number out in front here. Which means you would take the graph of x1 minus x2 times x1 minus x minus x1 times x minus x2 times x minus x3 and multiply it by some number in order to adjust the values so that you do get whatever this y1 is. And that would be either vertical stretch or vertical compression of this graph. So that's something that's well worth pondering. Don't have to do that. On the set of assessment problems that I handed out, you'll see problems where you have to do this. Okay. So you already almost know how to do it. There's no way I'm saying. Okay, well, there we have it. Now, to answer the quiz question, all you have to do is say the degree is 3 and why. Cool. It's got to be at least one greater than the number of turning points in the graph. It's got to be at least equal to the number of zeros. It's got to be at least one greater than the number of turning points. One other thing I'll say about it is this graph has a higher degree than 3. If you multiply all these out, you're going to get an x for this, an x for this, an x for this, and an x squared for this. That gives you an x to the 5th, doesn't it? So this would be degree 5. We would still have only these 3 zeros because x squared plus 36 can't be 0. X squared has to be positive. When you have 36 with a positive number, you're not going to get a 0, are you? Okay. And other possibilities. And this is degree 5, only 3 zeros. Now, if you were to graph this, it might end up with an extra turning point or 2. Maybe not. If you multiply all these out, you're going to get an x squared among other things here. You're going to get an x cubed among other things here, and an x here. Three six, you're still only getting 3 zeros. Now we investigate this question a little bit later in the chapter, but I want to mention it now so that when we get into it, you understand it a little bit in context of what you learned in the first section.